Keith Peters, welcome.
Yeah, thank you. Very happy to be here, Mark, too. Yeah, I met Mark the first Flash on the Beach, which is a conference in Brighton. It's all right. It used to be good. Yeah, so like you said, the last several years we keep talking about coming over here, and I'm really psyched to be here. I guess I only have 45 minutes, so I'm going to start plowing through these. I'm going to talk about chaos and fractals and strange attractors, and I guess there's another, I didn't realize this, there's another thing on fractals tomorrow, but this one's going to be better. Actually, I have no idea, but I'm sure they'll both be cool. So if you're into that, make sure you catch that one too. I first got into fractals many years ago with my Commodore Amiga. How many people have had that machine? Yeah, it's a great one. And it had this, fractal Mandelbrot Explorer, and I would just, be into that for hours, just exploring all the different things. And and later, when I learned how to program, I figured, well, I can actually program these fractals and stuff. I think there's two reasons I really get into fractals and this strange kind of math. One is that I just enjoy math. It's kind of like I like figuring things out and doing things with numbers. And I was really psyched a few years ago to learn of that this subject exists, recreational mathematics. I thought I was just the only one who liked doing math for fun, but I guess there's other strange people out there too. It has puzzles and games and different, logic things that you can do with math. And the other part of it is the algorithmic or generative art is like using numbers or using math or physics to create these really cool-looking images. So I've always had a little bit of an artist in me. I've never been a great designer, like putting things all together, but I love making things that look cool, and if I can use math to do that, it's a great combination. So we'll dive right into what a fractal is. Term goes around a lot, but in its essence, it's just a shape. A fractal is a shape. And unlike a simple shape like a circle or a square or a triangle or something like that, which is just, it is what it is, a fractal is made from other shapes. So you have, this one shape that's made from 3 different triangles. And each part of that shape is a copy of the whole. So you have that top set there, and the bottom 2 ones they're basically a copy of the entire thing. And then you keep iterating on that, making each part a copy of the whole. And theoretically, you can iterate fractals infinitely. Obviously, in the computer, you run out of memory, or you can't divide a number anymore because there's no space to hold a number that small. And in the physical universe, you have fractal forms as well, but of course, they break down at a molecular level at the very least, if not well before then. But when you're talking about them mathematically, you can't extend them into infinity. And the one we're looking at here is called a Sierpinski Gasket, and we can see this in all its glory here. So basically, you start with a triangle, and you form 4 triangles out of that, and you remove the middle one. And then you do the same thing on the next one, the next level, and you keep going like that. And, just about this point, we're down at the level where iterating more, you wouldn't see it because we're down at the pixel level. But if you could zoom in, you could keep zooming in, and you continue to get this form. And it's an interesting one because we'll be seeing this come up in other places. Happens to mysteriously appear here and there. This other one is called a Koch Curve, and it basically starts out it starts as 4 line segments, across, up, down, and across. And then you take that whole shape and you replace each segment with that whole shape. So you get that, and then you replace each one of those with the whole thing, and you get that. And as you keep going like down there, you get that. And we have that as well, so you can see that. And again, we get down to the level where we could keep iterating, but you wouldn't really see it because the pixel level can't show it. Now, if you took 3 of these and you arrange them in a triangle and you iterate it all the way through, you get what's called the Koch snowflake. And that has some interesting properties, which we'll see in a second. But first, we'll talk about the length of fractals. And that's another thing that will come up in a little while, too. But if we take that first iteration where it's just 4 line segments, and we consider that each line segment has a unit length of 1, then you could say the length of that top curve is 4. After one iteration, each one is one-third longer than it originally was. So the whole length of that second curve is approximately 5.3, rounded off. Do another iteration, and it's around up over 7. So it's almost doubled in length, just over 2 iterations, right? Now, if you carry that out, after 20 iterations, this curve up here is almost 1,000. So if you take, this is, a couple meters long, this would be like almost 2 kilometers long if you were to follow each little curve, just after 20 iterations, right? Which is a little bit crazy. And if you see this red curve that goes up, this is the length compared to the number of iterations. And remember we said that fractals can be iterated infinitely. So as you see, as this goes towards infinity, the number of iterations, the length becomes infinite. So this becomes an infinitely long line. And then you get this paradox here with the snowflake where you have the perimeter of this shape is infinite, theoretically. But the white area that it is filled with is finite. So if you were to draw a circle around that, you could find the area of that circle. The white area is less than that, so it's finite area, but the border is infinitely long. So you have an infinite border with finite shape in it. Here's another paradox, the Sierpinski gasket. Each time you iterate, you're multiplying the number of triangles by 3, and you're also reducing the area by 1/4. So as you tend towards infinity, you have an infinite number of triangles, and the area goes to 0. So I don't know how that works. These things keep me up at night. Here's another famous fractal. A lot of people have probably coded this, early on in graphic programming in Flash. It was a common one to do. You just take a tree, you get a stem with 2 branches, and you replace each branch with a copy of the tree, and you do that again, and you do it a bunch more, and you have something that looks kind of like an actual tree. You can kind of see a realistic kind of tree shape. But the problem with this is it's too perfect, right? And that brings us into symmetry and regularity. So earlier I said that so a fractal is a shape that has parts, and the parts are copies of the whole. Well, they don't have to be exact copies, right? They can be approximate copies. There can be some variation. And this one here, they're exact copies, and it's very symmetrical. But we can break the symmetry there. So now the 2 angles of those branches are not exactly the same. And so you get this kind of this leaning over feeling. And this actually looks a bit more real because, trees aren't exactly symmetrical, right? They're a little more organic like that. And then you can break the regularity. So each time you iterate, you're not replacing an exact copy of the whole, but you're changing it a little bit. So you have a little bit of random, the angles are a little bit random. So this actually looks, a lot more realistic, like what a tree would look like. It's still very stylized, but in terms of the way the branches happen, that's really more what a tree would do, right? So we can have an example of this. So let's see. So that's like perfect symmetry. So as we iterate that, we have a nice, perfectly symmetrical tree. And then we have a non-symmetrical tree. So that one kind of curves over like that. Let's see. So we just have these, various kind of trees. These are all regular. So each copy is a perfect copy of the whole, but the symmetry's gone there. That's a fun one. It's a good programming exercise if you want to start to think about fractals, like how you would draw something like that. Then we have the Pythagorean fractal. And this comes from the Pythagorean theorem, which states that if you have a right triangle with sides A, B, and C, then A squared plus B squared equals C squared. You all remember that from high school, right? Or you should. And we can demonstrate that by actually drawing the squares. So you have the two smaller squares. If you added up the area, it would be the same area as the larger square there, right? Now, if you were to flip this on its side, we have a shape like that. It's the same thing, it's just turned. And you see that kind of has the same form as a tree. So we can actually fractalize that in the same way we did the tree. And, damn, why does not link work? Okay, 1 second here. One link can screw up your whole day. There we go. All right, so we have the square, and that middle triangle doesn't have to be a perfect triangle in terms of like a 45, 45, 90. It can be really any angle as long as that top angle is 90 degrees, right? So if it is kind of almost there, and we iterate this, so what we do is we take that square, we put the same triangle on top of it and square the sides, same one and that one. So we have a copy of the whole shape, and then we do that again and again. We do some fancy coloring, and we have this Pythagorean tree. It looks nice, large. And if we have a more slanted triangle like that, then you have this more slanted tree like that, and you have this nice spiral going around here. It's a little lag there because it has to draw so many squares. And the funny thing is, about this is when you think of like these top two squares here, the first level, are equal to that large square. And if you look at the next level, the next 4 squares, maybe we can just start this over. So those 2 squares are equal to the bottom square. And if you iterate, the top 4 squares equal the next 2 squares, so all the top 4 squares also equal the size of that bottom square. And if you keep iterating that out, so all the end squares, all these ones here, if you added all those up, they would fit into the bottom square. Kind of a neat thing. All right, so we have the Mandelbrot set, and that was named after Benoit Mandelbrot. And in a essay once, he asked the question, how long is the coast of Britain? Which seems to be a pretty simple question, right? Pretty simple answer. You take a map like this and you just outline right around the coast, right? And you come up with a number for how long it is, right? Very simple. But say you had a larger map and you could kind of zoom in. Well, now you're like actually getting into like these little inlets here. And when you measure it, you're measuring like little ins and outs that you didn't measure before, and you'll actually come up with a larger number. It's a more accurate number, but it's always going to be larger. The more you measure, the larger it's going to be. So the answer to the question of how long is the coast of Britain is it depends on the size of your measuring stick. And we can kind of simulate that here. So we have this line going across here. And what we're going to do, actually, if you look at the number up there, it's 1026, right? And that's how long that line is in pixels. So the monitor is 1024. It goes 1 pixel on each side. So that line is 1026 pixels long. Now what we're going to do is we're going to break the line in the middle here, and we're going to raise it up or down or kind of randomly around somewhere, right? So now we have 2 segments. And you notice the length went up a little bit. And now we're going to break each of those segments and randomly displace those points and do that a bunch of times. And you see now our line is about 1,200 pixels long. And if we want to, you can actually use this like if you're creating a game that you need to create like a landscape or something like that. You just color that in and you have a nice kind of realistic landscape, programmatically generated. It's going to be different every time. And, you can generate a different one here. Keep doing that, right? The other thing to look at is this number up on the left-hand side of the screen. That's how bumpy this thing is going to be. That's how much the randomness scales on each iteration. So if we up that a little bit, and now we iterate, it's going to be a much more jagged coast. And now look what happened to the number up there. That number's gone on to over 6,000. So if you to follow this coastline all the way along, it'd be 6,000 pixels long. And when you figure this screen is only 1,024 pixels wide, it's pretty crazy. It goes back to like the Koch curve we were looking at. It's like it just gets longer and longer the more detailed you get for a measurement. So we can do the same thing. We can make it an island, right? And just the kind of same thing. We'll bring that down a little bit. So we have an island. It's great for generating procedural landscapes, right? If you're doing some kind of game, mapping game or something like that. And again, you can see we start off like around 1700 is the perimeter of this island, but within a few iterations, it's like 3 times as long as it was, right? Pretty neat. So related to this was someone named Richardson, and I should have figured out what his first name was, but he noticed this, and he kind of mapped out different areas of the world based on, so you have a certain scale map, you measure it, and then you increase the scale, you're getting more detailed, and you measure it. And like I said, that'll keep the different the scale, the longer the measurement will be. And he found out that different parts of the world have different slants of that line for the logarithm of the scale of the map based compared to the measurement. And this is called the Richardson Effect. So like, you see Great Britain there has really the deepest slant, which means it's the most jagged. It's the most, as you measure closer and closer, you're going to get longer and longer distances. And that brings us to the subject of dimensions. So we all know like one-dimensional objects and two-dimensional objects. A line has one dimension, it's just the length, right? Something like a square, triangle, circle has 2 dimensions, length and width. But when you get into fractals, we actually have dimensions in between 1 and 2. These are called fractal dimensions. And you can actually measure things like coastlines as fractal dimensions. So something like the south coast of Africa has a dimension of 1.02, which means it's pretty smooth. Whereas something like the west coast of Britain is 1.25, which means it's very fractally or jagged, very close to what the Koch curve is at 1.26. And then the Sierpinski Gasket is 1.58, which means it's very fractally. It's a really interesting thing. I don't have time to get into it, but if you study, you just do a search for fractal dimensions, and there's all kinds of physics on like what something would weigh if it's a fractal, and like based on its length. So it's not just this theoretical thing. There is an actual partial dimension there, which is kind of freaky. Next thing we're going to talk about is something called a chaos game. And this is an example of how order can arise from chaos. And it starts out, we're going to choose 3 random points. I've kind of arranged these nice and symmetrical, but any 3 points are going to form a triangle, right? Then you choose a 4th random point, anywhere on the screen there. And you're going to go from that point, you're going to choose one of these other 3 points randomly. Doesn't matter which one we choose. And we're going to draw a line to it. And then midway on that line, we're going to create a new point. Now we're going to take that new point, and again, we're going to choose one of the original 3 and draw a line to it and add a point there. And we're going to keep going and going and going. And most people will imagine that eventually you just have a solid filled square, right? Because you're just adding random points within these points. But what you actually get is a little bit different. So, oh good, you can see those points pretty well. So we just create 3 random points there, and then we'll throw another point in the middle randomly, and then we'll randomly choose a point, draw a line, add a new point, choose another corner. Can you see those red lines? No? Can we turn down the lights maybe a little bit? Or maybe we can't. There we go. Okay, maybe you can just barely see that red line, right? So we choose another one, and another one, and sometimes it chooses the same one a few times in a row because it's completely random. And then me pressing the space bar is kind of annoying, so we'll just speed this up. And we'll just let it run for a while and see what it creates. So you can probably start to see it now. It's the Sierpinski Gasket again. And it's kind of a neat form because you'll see this coming up again and again. There's like so many ways to create this. Like, you know, maybe you've seen this before, but I never would have guessed that it would have created that from those simple set of random rules, right? There's another, if you guys familiar with Stephen Wolfram, wrote a book called A New Kind of Science, and it's got this cellular automata. So you start with a row of pixels at the top, and based on different rules, you create a new row of pixels next to that, and a new row of pixels based on that pixels. And there's one rule that will, again, create this same picture. So it's this image that keeps coming up again and again. Similar example to the chaos game is something called the Barnsley Fern. And the way this works is, again, you start with a random point, which is right there. And then we have a set of, I think, 4 rules. And we're randomly going to choose one of these rules. And what each one of these rules does, it's a transformation matrix, which means it can scale this point, it can rotate this point, and it can translate this point, each a certain amount. So when you have one rule that says, okay, I'm going to rotate this so many degrees, translate it so much, and scale it. So there's 4 different rules with exact numbers in them. And each rule is weighted, so some rules will be applied more often than others, but each time we're going to randomly choose one. So we're going to randomly choose a rule, apply it to that point to find a new point. Okay, so we chose a rule that's going to translate it down and maybe rotate it a bit and scale it or something like that. I don't know exactly what it did there. And then we do another one, another one. And you see, the one that kind of makes it go up and slant off to the right is probably the one that's weighted the heaviest, because you can keep seeing that kind of thing happen again and again. And again, if we let that go, just randomly choosing a rule each time, it creates this image. It's called the Barnsley Fern, which I guess is actually there's an actual fern that has this exact shape too. But Barnsley is the guy who named this particular set of functions. This is a very fractal image, because if you look at each piece of the fern, it's actually an exact copy of the whole fern. Some of them are flipped around. And then each one has, you see this little piece here is an exact copy of the whole. And if you were to zoom in and render this at a high enough resolution, it would just keep going infinitely, regressing with additional copies. Then we have another one. This is a tree fractal. It's the exact same setup, but this one has 6 different rules. Again, transformation matrix, scale, translate, rotate, random points. You don't really see what's happening until you do it real fast. And it generates this tree. And unlike the trees we saw before, this is actually kind of like something you'd expect to see, as a silhouette of a tree. It's actually pretty realistic looking, right? A little variation on this. Each time I choose one of these 6 different rules, I'm going to color that pixel a particular color. So you see we have the 6 different rules here. Let me keep the lights down for a little while. They don't need to see me. This is much prettier than me. So you have 6 different rules. You have the green rule, which creates the trunk here, the red rule, which creates another part of the trunk, and you have the other 4 rules, which create other entire copies of the tree. And when you put it together all like this, it looks like somebody cut out a bunch of trees from a magazine and pasted them together. It looks not so natural anymore, right? But if you do it without the coloring, it looks very natural. So, and these are all, you can actually mess with the numbers in the rules a bit and actually come up with different types of trees. And all this, I'll give you a link at the end. All the source code for this is all done in JavaScript and Canvas. And so this will all be up online, and you can kind of go mess with it, play with it. Diffuse limited aggregation. This is another I'm going to just start this one because this takes a little while to build up. So what we have is we have a bunch of particles. They're floating from the top down to the bottom. They have kind of random velocity. When they hit the bottom, they stick. Or if they hit another particle that's already stuck, they stick. But rather than just kind of piling up in one big pile, what happens is you get these kind of tendrils, these kind of looks like coral forming or some kind of plants growing. That's because like you get these little areas down here of this space, and it's pretty hard for a particle, oh, that one just did, to like fall all the way down to the shape. But most of them are going to land on top, so you get this fractal form building up. And if you were to like, again, render it this at a high enough resolution and zoom in, you'd find that each little part of this, of each one of those forms has the same form. It has these little tendrils that will kind of reach out. And we'll be seeing some other stuff that looks very similar to this. It's the thing, you can study all different kinds of fractals in math or computer or in the real world, and you see the same, very similar forms showing up again and again, like the Sierpinski Gasket and these kind of tendril-like shapes. And then we get to the holy grail of fractals, the Mandelbrot Set, which I'm sure you've all seen. It's named by Benoit Mandelbrot, and he started out as an economist, and he was studying how economies work and the cause and effect of money systems and stuff like that. And he found some very strange things that weren't really described by a lot of mathematics. Then he went into different fields of math and physics and stuff, and he saw the same kind of things happening, especially in natural forms, these same kind of patterns happening. And he developed this whole fractal science field. He's best known for the Mandelbrot Set. And so we're going to do a quick run through on how you generate the Mandelbrot Set. First, you have to know what an imaginary number is, and that's a square root of a negative number. So obviously, any number times itself is positive. Like -2 times -2 is 4, not -2. So it's impossible to come up with a square root of a negative number, but it happens that they're very useful in a lot of engineering and mathematical functions. So we define I as the square root of -1. So then if we have the square root of -5, that can be extracted out as 5i, right? Then we have to know what complex numbers are, and that's just a real number such as 4, plus a complex number like 5i. Very simple. Then this is the Cartesian plane, which I'm sure you're all familiar with. We have x on the horizontal axis, y on the vertical axis, and you can plot numbers, 4, 2, xy, 4 on the x-axis, 2 on the y-axis. If you're dealing with screen coordinates and pixels, usually the y-axis is upside down because that's how they did it when they first made TV, and we've always followed along that way. But we can take the same kind of thing, and we can map real and imaginary numbers onto it, and this becomes what's called the complex plane. So we have a number like 4 plus 2i, where we map the 4 part on the real plane, on the real axis, and the 2i part on the imaginary axis, and that's how we can plot out imaginary numbers. So to generate the Mandelbrot set, this is the whole formula for that entire bizarre construction. It's z prime equals z squared plus c. So you have a value of z, and you have a value of c, square z and add c, and you get a new value for z. And then you keep doing that over and over and over. I know. Maybe I should say z, but I'm American, so I say z. So you keep doing that over and over, and you get a result each time, and then you do that for the entire picture. The thing to know is that z and c are complex numbers. So each one has a real and imaginary part. Each time z begins as 0, or 0 plus 0i, and c is a point on the complex plane, which we'll see that more visually in a second. And you iterate each time over and over for that particular formula. And as you iterate, one of two things is going to happen. Z is eventually going to go way off into infinity. in which case you color that pixel. Usually what happens is basically how fast you saw it go off into infinity. Maybe if it went out there really slow, you color it red. If it went out really fast, you color it yellow or something like that. The other possibility is that Z doesn't go off to infinity. It kind of stays in a particular range. It doesn't go crazy. In that case, it's part of the Mandelbrot set, and we color it black. So to see that visually, we have our complex plane here. And we start over in the upper left-hand corner, so that's -2, -1i, so that's how we plot that. And that's going to be C, so that's going to be constant. And then Z or Z is going to be 0. So we multiply, we square Z, which is 0, we add C to it, and we get a number, and we keep doing that over and over. And we find that that's going to go off to infinity. So we color it whatever color we want. Then we move to the next pixel over, and that's mapped to a different C value. We do that over and over. We do that for the entire screen, and we get this shape here. And we can see this in real life, actually generated in real time. And this is all done in Canvas and HTML5 with JavaScript. So I was pretty amazed how performant I got it. Because I remember back when I was first doing this Amiga, you'd like zoom in and you like wait for like 3 minutes while it rendered, So I was pretty amazed at how fast I could get it in Canvas, just straight up Canvas and JavaScript. So you can kind of zoom in on these things. I guess the guy who's talking tomorrow has actually done some stuff with OpenGL, which I'm sure is a million more times faster than this. You can probably do real-time zooming. But you can kind of zoom in, and people have like actually named these areas, like the Valley of the Seahorses is in here somewhere, right? Or maybe I got it backwards, and the Valley of the Elephants is somewhere else. And these different forms that come up, and it's kind of, anyways, this will be online. You can play with this or make your own. Another favorite of mine is strange attractors. This is something I play with a lot. Without getting too much into the math, you have these are often done in 3D. So you have a formula for X, Y, and Z. And you have a point, an X, Y, Z 3D point, and you apply formulas to each of the X, Y, and Z, and you come up with a new point, and you plot that, and you apply the formula again, you plot that. So you end up with a whole bunch of different points. So usually 3 different things can happen. One is that you just get points everywhere. You get a big explosion of points going off to infinity, and just total chaos and randomness. The other possibility is that it settles in on like a few points, and from there on, all the points just go on, and you wind up with like 2 or 3 clumps. But if you get the values just right, and the formulas just right, you get these really amazing shapes. And so you have something like this. And again, I was pretty surprised. This is like 50,000 particles rendered in JavaScript in real time. Without a whole lot of optimization, I could probably spend hours optimizing it way more. But there's like 5 parameters that go into making this shape. So we can start messing with these and get all these different shapes. And I don't know, I could just mess with these for like hours and probably have. And you can kind of zoom in and zoom out. I could probably spend the rest of the presentation just playing with this, but I have more slides, so I'm going to move on. Another strange attractor is called the Lorenz Attractor. Actually, the formulas we were using on the last one were a variation of the Lorenz Attractor, but this is the classic Lorenz Attractor, and this was named after Edward Lorenz. He was a meteorologist studying weather, and one of the things you study is like gases have these 3 properties: the pressure, the volume, and the temperature, that all interrelate. So if you raise the temperature, the volume increases, the pressure increases, and so forth. And he figured out these particular values that, if plotted, would give this very strange, interesting shape. And they're attracted to these 2 points. So it'll like spin around and circle this one orbit, and then it'll randomly jump over and start orbiting this other space. And this is actually 3D. It's not rotating or anything, but you could actually view this from any angle, and it's this really beautiful shape that comes off. Sometimes called the butterfly attractor because it kind of looks like the wings of a butterfly. Again, all the source code is up there. You can check it out and learn from it. And all right, we're doing pretty good on time. So fractals in nature. So Benoit Mandelbrot, he's the kind of known as the father of fractals. He developed the term as well as a lot of the science and thought that goes behind it. One of his books was The Fractal Geometry of Nature. And that's one of the things, when you look in nature, you see these fractal forms over and over again. And this is obviously a close-up picture of a leaf, but if you didn't know any better, it looks an awful lot like the zoom in of the Mandelbrot set, right, with these different branches going off. This is an area of wetlands near where I live in Boston, in Massachusetts, in the United States. This is up New Hampshire, a few miles away from me. And I think this is pretty cool. This is just a Google Earth image. But you have the natural curving of the naturally curving rivers. Then in here you have like these man-made, like straight orthographic lines. So it's kind of this natural plus man-made fractal kind of thing. This is one of my favorites. This kind of looks like an electron microscope vision of some fungus crawling across this plane, right? What this actually is, it's a trick of the light. These are actually valleys and mountains in an area of East Russia called Kamchatka, I think it is. Anyways, my wife's from Japan, and we fly over there, and we fly right over this area, and I saw this like really weird geography. I looked it up on Google Earth, and actually these green areas are actually valleys. It looks like it's kind of something snaking along the top of something, but if you kind of zoom in and tilt it, you see that these are actually valleys, and the white areas are mountains. But I thought that's a really cool thing. This one, anyone have any guess what this might be? Now, this is called a Lichtenberg figure. What they do is you take a square piece of lucite, which is like a clear plastic, and you fire about 50,000 volts of electricity into it. People have nothing better to do with their time. And as the electrons zoom through, they melt the plastic, and they form these bizarre shapes. And it's this fractal branching because the electrons want to repel each other, so they're always like moving apart from each other. And so they just branch out fractally, and this is actually, I left it at the hotel, but I'll be around tomorrow and I'll bring it. It's it's about that big, about 6 by 4 inches. And this is actually a picture of the one I own that I took with a close-up lens. And you can actually examine these things with a microscope, and this branching goes down to like an atomic level, actually, because it's electrons zooming through this thing, so it's actually branching probably about as much as you're going to see a man-made fractal branch. And this is another one of my favorites. This is something called a Romanesco. I don't know if you guys have ever seen it. It's kind of like a cauliflower or broccoli. And it's actually edible, believe it or not. And it's composed of these nodes that are formed up in a spiral. And if you look at one of the nodes, it's composed of these nodes that are formed into a spiral. And if you look at one of those nodes, it's composed of these nodes that are formed into a spiral that are composed of nodes and nodes. And eventually it kind of breaks down because the cells kind of lose their definition to make more spirals and nodes, but it's kind of freaky. I don't know if I would actually eat this. I don't know what it would do inside me. But just to close on a quote from Mandelbrot, it says, "Clouds are not spheres, mountains are not cones, coastlines are not circles, and bark is not smooth, nor does lightning travel in a straight line. Nature exhibits not simply a higher degree, but an altogether different level of complexity." So I challenge you, like when you're out walking around, looking at trees, or mountains, or the cracks in the pavement, or just different things in nature that you see, you're going to start seeing these fractal forms, and just kind of take a look and try to see them, and again, play with the code. That's the URL. You find all the examples there, along with a PDF for the presentation. And it's all JavaScript, so you can dig right down into the code and play around with it and have fun. Thank you.